Last time we talked at length about one, sort of the, dealing with a geometric series in general. And what we showed was that this formula that's sitting right here is actually more general than they make out. Like it's starts, n equal to m, and this would just be ar to the m up here. That's how that would change. Essentially, the first term is what sits in the numerator of the formula for geometric series, right? So this right here is the first term. And we kind of talked about that. And we also talked about telescoping sums last time, right? And telescoping sums, we had things looking like this up here. Yes, telescoping series. We talked about the key is to look at the nth partial sum and then to take the limit as n goes to infinity, yeah? That's the safest thing to do in those cases. And I mentioned that for a while, these are going to be the only two types of series that we can say definitively what they add up to, if indeed they happen to converge, okay? So any questions on telescoping and geometric series? Any questions? Well, here's a couple of facts you can take to the bank. So first of all, if you ever have a constant multiplied by every term, see this? So you have this constant multiplied by every term sitting right here. What do you think you can always do with that constant? You can pull it out. After all, this is a sum, okay? So you can pull that constant out. So that's what that first fact is saying. And if I ever have a sum of, and like every term is just a sum of two terms, you can break up the sum. Does that make sense? And kind of break up the sum as well into the series an plus series bn. So series an plus bn is equal to series an plus series bn. That probably isn't too surprising to you. Now, we're going to start talking a little bit more loosely about kind of the notation of series, because does it really matter whether I start at 1 with a series or not? Do I have to start with n equal to 1? Does the first term always have to be a1 necessarily? No, because when you talk about convergence of a series, the first so many terms don't really matter anyways. Those are clearly going to add up to some finite number, yes? The question is, what about the last infinitely many terms? What do those add up to? So a lot of times you'll do things like this with the notation. You'll just say, series an, and you don't really specify like where n starts, and you just know that the series, that n goes off to infinity, yes? So you can just write the sum symbol, and it's understood that you mean that this is like an infinite series, okay? Okay, and this is a very important fact that I think some of us have already talked about. If the series is to converge, then eventually adding terms on like way out in the series had better be like adding on not very much. Does that make sense? So like I add a bunch of terms together, and eventually it better be like I'm adding on things that aren't contributing very much. Otherwise, the partial sums won't converge, yes? Right? When I move far out into the, the sequence of partial sums, those things need to be getting close to a number, right? If I have convergence. And that means that I better not be adding very much on at all. Does that make sense? Eventually, I better not be adding on very much at all. What that means is the terms themselves need to be going where? The terms should be going to 0. Okay? So the terms need to be going to 0 if the series converges. If the series converges, the terms had better be going to 0. That will simply take care of this business that we just mentioned. Namely, eventually it will be like I'm not adding on very much at all. So that's definitely something that's necessary in order for the series to converge. So series converging makes it necessary that the terms tend to 0. Okay, terms tend to 0. But the other way around doesn't work. Just because the terms go to 0 doesn't guarantee what? that the series will converge. Okay? The terms go to zero. That does not guarantee convergence. Okay? But if the terms don't go to zero, what do you think you can say? So like, look at this. The so-called contrapositive, it's kind of a logical statement, says that if the terms don't go to zero, then the series has to diverge. What that means is, look, if you want to have a chance to converge at all, what has to be happening to the terms? Well, if you want to have a chance to converge, the terms have to go to zero. So if the terms don't go to zero, what? Then convergence is not an option, yes? If the terms don't go to zero, then convergence of the series is not an option, okay? You're simply going to be adding on too much, or you're going to be adding on something unpredictable or something. So the terms going to zero is a necessary condition for convergence, but it doesn't guarantee convergence. It's not sufficient for convergence of the series, okay? But you have to be careful here. So if the terms don't go to zero, you know the series can't converge, i.e. it has to diverge. But if the terms do go to zero, what do I know? It might converge. The series might converge. There's a chance it might converge, okay? So you have to be careful about how you apply this. By the way, this thing right here, this theorem right here is called the Nth Term Test. Nth Term Test for convergence. Okay? And basically, the Nth Term Test is oftentimes applied in this way right here. If the terms don't go to zero, you automatically know there's no chance to converge, yes? Terms don't go to zero, there's no chance to have convergence, okay? But if the terms do go to zero, you conclude nothing, excuse me, right? If the terms do go to zero, you just know there's a chance that you might have convergence, but you might still have divergence. So look at this. This one right here is pretty famous. This is oftentimes referred to, I think I already mentioned this. This is oftentimes referred to as the so-called harmonic series. Harmonic series. Okay, and it turns out that the harmonic series actually diverges to infinity. But what do you notice about the terms? So this thing diverges, but what do you notice about the terms themselves? What do they go to? The terms go to zero, and yet the series does what? Diverges, okay? 1 over n, right? The sequence of terms, 1 over n, this goes to zero, but the sum, 1 over n, diverges. Okay, so this is the thing that flies in the face of what you might be tempted to conclude. Namely, you might be tempted to conclude, every time the terms go to zero, that means the series converges. No, that is not what happens. But if the terms don't go to zero, then convergence is off the table. The series necessarily diverges. Okay? Okay, please ask questions about this. This is like our first official test for convergence that doesn't have anything to do with determining a sum like telescoping and geometric did. So please ask questions about that. Questions? Any questions? Okay. So if the terms don't go to zero, what can you conclude? Series does what? Diverges. If the terms go to zero, what can you conclude? Nothing. Okay? Okay, you're going to have to resort to some other method to determine convergence or divergence. But if the terms don't go to zero, then you know there's no chance for convergence. Series diverges. I'm saying this over and over and over again because this is one of those issues again where it's like I've seen students over and over and over again apply this test incorrectly. They'll say, oh, look, the terms go to zero, therefore series converges. No, okay? That is not what you're allowed to conclude. The harmonic series is a counterexample, yeah? The terms go to zero, but the series still diverges, okay? Please, questions. Okay. So let's talk about this series right here. Look at this. Sum n going from 1 to infinity of n over 2n plus 3. Yeah. What about those terms? What do those terms go to? Well, I kind of wrote it right here. Do you realize those go to 1/2? Yes? So since the terms don't go to 0, since the individual summands do not tend to 0, what do you conclude about the series? Series diverges. Because what this means is essentially for large n, like n equal to a trillion and 1, etc., basically that's like adding the number 1/2 over and over and over again. Does that make sense? It's like you're just adding 1/2 over and over and over again. And clearly, that's going to cause the sum to diverge, right? Adding 1/2 over and over and over again is going to cause that thing to add up to infinity. Okay? Any questions on that? Okay. All right, so please, don't forget this is called the Nth Term Test. The Nth Term Test. If the terms don't go to 0, you immediately conclude divergence, and that will probably be sort of in the the hierarchy of tests that you use. Usually what you'll do is you'll say, oh, that's a geometric series, or oh, that's telescoping. And if neither of those, the first thing you typically try is the Nth term test. You check to make sure that the terms go to 0. If they don't go to 0, what do you immediately conclude? Diverges. The series diverges. If the terms do go to 0, then you're going to have to go deeper into the toolbox of convergence tests that we're going to develop over time. Does that make sense? We're creating a hierarchy. First thing you do is you say, is it geometric or telescoping? If yes, do your thing, right? If no, try the Nth term test. If the terms don't go to 0, diverge. If the terms do go to 0, then you need to go deeper. You're going to have to figure out what's going on in terms of divergence. Okay? Convergence or divergence. All right. So what I want to do now is I'm going to pull up a PowerPoint presentation here called the integral test. Okay? Here we go. The integral test in P series. Okay? Essentially, this is the integral test right here. It says, if f is positive, continuous, and decreasing for x greater than or equal to 1, and basically the function equals the terms at positive integer values. That's what that little statement says right there. So an is equal to f at n. So the function is equal to the term values. So like for instance, maybe f of x is equal to 1 over x. And our terms are like 1 over n. Does that make sense? That would be an example of this sort of thing. Then the series and the integral behave exactly the same. Okay? If you find yourself in this situation where the function is positive and decreasing and continuous, and it basically has values equal to the terms, like on the positive integers, then the series and the integral behave exactly the same. And by the way, do you think it's very important that everything start at 1? Do you think that's important? Nah. I mean, look, this could be x greater than or equal to, some number, b or something like that. And this could be n equal to b, and this could be the integral from b to infinity. Does that make sense? It just has to be from some point on. The function is positive, decreasing, continuous. Okay? By the way, how do you check that a function is decreasing? You take the derivative, yeah. You take the derivative. Yeah. Okay? So these two things are going to converge or diverge together. And essentially what's going on here is you have a function that looks like this. Okay, so They said 1, but we know that, that's not all that important. So the function kind of starts, here, and it's positive and decreasing. So it's basically looking like this. This is the graph of y equal to f of x. And essentially what's happening, okay, is, this guy right here, this value right here is like a1, at 2, the value of the function here is a2, okay, 3, go up here, this is like a3, etc. Yes? That's what's happening here. Okay, so in essence, f of any n is just equal to an. That's what this little assumption is in the integral test. Okay? And how in the world can we see that these things converge or diverge together? Well, basically it amounts to this. Look, what I can do is like, suppose the integral diverges, okay? Suppose the integral diverges from 1 to infinity. What does that mean about the area under the curve? What would that be? If it diverged, what would the area under the curve be from 1 to infinity? Right? If that area right here was plus infinity, why does that mean the series also diverges? Well, it's because of this. I could actually make some little rectangles whose area is actually bigger than the yellow area under the curve. Does that make sense? And what's the height of that first rectangle, everyone? It's a1, and the width is 1. Does that make sense? And what about the height of the next rectangle? a2, the next rectangle, a3, etc. Does that make sense? The areas are a1, a2, a3, and the area equals the sum of the a's, right? The area of those rectangles is going to be a1 plus a2 plus a3, and that area, which is equal to the sum of the terms, is bigger than the yellow area, which is already infinity. Does that make sense? Which is already infinity. Now, so if the area of the, so if the area under the curve is infinity, then the series also has to equal infinity, right? So integral diverging implies series diverges, yes? What if that area is like not infinity? What if that area is like, I don't know, what if it's not infinity, but it's like 5 or something? What if this area under the curve was like 5? That is, it's something finite. Well, in that case, what you can do is this. You can actually say, look, I'm going to make some different rectangles, okay? Okay, just give me a minute. I'm going to make some black rectangles here. Here's the first rectangle right here. Okay, so here's the first rectangle. What's the height of that rectangle? A2. Here's the next rectangle. What's this rectangle? What's the what is the height of that rectangle? A3, then A4, etc. And now you see that the black rectangles have area, what? Bigger or smaller than the yellow? Smaller. And since the yellow area is already finite, and I'm like just adding up, right? I'm adding area in the black rectangles every time so that it's kind of the sequence of partial sums getting bigger and bigger, but it has a ceiling, right? Namely, the yellow area has an upper bound. So by the monotone convergence theorem, remember that thing? By the monotone convergence theorem, the series would have to converge also, yeah? So if the integral converges, the series has to converge, yes? If the integral diverges, what happens? Series diverges, and all of it has to do with this little picture I just drew, either using the blue rectangles or the black rectangles, depending on the situation you find yourself in. I'm just justifying why this test works. You don't have to memorize this like proof or anything. Does that make sense? I'm just trying to give you a justification for why this happens to work, okay? So these two things behave exactly the same in this instance. If the function is positive, decreasing continuous, and it equals the series terms on the positive integers, then the integral and the series behave exactly the same. Okay, any questions on that? Yeah. It's not, I'm not considering the Riemann sum. The Riemann sum, I would let the bases get smaller and smaller. Does that make sense? I'm not trying to, what I'm doing is I'm just saying, I'm going to create rectangles whose area happen to be equal to my terms, like A1, A2, etc. Does that make sense? So like in this case right here, you know, this is like A2, A3, A4, basically, right? Because this is 4 right here, etc. Yes? And if that yellow area was finite, then the black rectangular area would have to be finite also. But the black rectangular area is basically the series. I don't have the first term in there, but who cares about that, right? Now, what about the blue area, though? The blue area, you know, that's like A1, A2, A3. That blue area is actually bigger than the yellow area. Does that make sense? It's funny, like you can basically just by getting rid of the first term, you could either be above or below that integral area. Okay, so by including A1, that yellow area is below it. So if that yellow area is infinite, then the series has to be infinite as well. Yeah? On the other hand, if that yellow area is finite, the black area guarantees that the series will also have to add up to something finite also. It will converge. Does that make sense, Maria? So there's no Riemann sums, all right? No Riemann sums. It's just, you know, each one has base length 1 here. Yes. No, no, that's okay. So do you see how the yellow area here is like it's not exactly the same. It's not exactly the same as the blue or the black area. Does that make sense? Like in the case of the black rectangles, the yellow area is a little bit bigger than that, yes? And in case of the blue rectangles, the area of the blue rectangles is a little bit bigger than the yellow area, yes? So whatever the value of the integral is, isn't going to be the same. If it happens to be finite, it's not going to be the same as the series. It's going to be off a little bit because we're approximating. Does that make sense? So this is what I mean by we don't know what the value of the sum is in the case of convergence. We know what the value of the sum is in the case of divergence in this case, right? What would the value of the sum be in the case of divergence? Infinity, yeah? But in the case of convergence, we can't tell because we're approximating things. Does that make sense, David? Yeah. Okay, other questions? Yeah.
So if you took the blue squares on the finite amount, so like 5, but then the sum would be like equal to rectangle square, the blue rectangles, why wouldn't that make the sum indeterminate, or like the convergence indeterminate because the squares are bigger than?
Well, yeah, right. So what you're saying is, okay, look, I don't like, it seems like it seems like you're playing some kind of trick on us. It seems like all you're doing, like you're in one case putting the blue, like one extra term in there and it's suddenly bigger than the area under the curve. That's true. Yeah. But I can also just slide, all I've done in the second case is I've slid the rectangles over. You see, I've kind of slid the blue A2 rectangle over. And that first rectangle that was A1, I'm just kind of throwing that out, right? I'm just looking at it from one perspective or the other, dependent upon what situation I find happening with the integral itself. If the integral is infinite, then which situation do I want to look at, Daniel? The blue rectangle, yeah? Because that will cause the overall sum to be infinite, yeah? If I find that the yellow area is finite, what situation do I want to look at? The black rectangles, in which case, and that sum is finite, yeah? And so if I slap on A1 at the beginning, it's still finite, right, Daniel? Yeah?
It seems like it seems like you say the integral is infinity, so therefore you take a situation that looks favorable to the integral being infinity.
Yeah, I don't deny that. We're definitely doing that. Yes. But why is that a false
Well, I
presupposition?
guess not false, but like it seems like both situations could be true at the same time. So the blue and the black.
Well, yes, the black rectangles could also add up to infinity. Yes. Right. But the way that you kind of see that they do is by putting the first term back in, and you see that the area of those is actually bigger than the yellow area under the curve. Yes. Yeah. So I mean, you're kind of just either including the first term or not including the first term. So yeah. Okay. So yeah, that's good. That's a good little philosophical discussion. It's good. All right. So other questions? Other questions? All right. Well, let's keep going. Well, okay, here's a couple of notes, which I think someone's already pointed out. If both converge, they probably converge to different values. This is getting back to David's question. Why? Why, if they both converge, why do they conclude, why is it probably true that they converge to different values? I already erased the picture, but you saw that the yellow area was clearly different from the rectangular area. Does that make sense? Okay. Leaving off a few terms at the beginning doesn't change the convergence or divergence of the series, yes? Which is why we don't necessarily freak out if this started at some number B or something, okay? If this was B and this was B and this, you know, this positive decreasing thing happens starting at B, okay? As long as f is positive, continuous, decreasing, eventually the integral test will apply, okay? So the integral and the series converge or diverge together, okay? Now, I want to talk about P series, and I'm telling you, we've already talked about this before. Okay, what is a P series? Well, it looks like this. Sum n going from 1 to infinity of 1 over n to the P. Okay? That's why it's called a P series. So P is like the power on n, okay? Now, what about 1 over x to the P? Is that a positive decreasing? So think about it. F of x equal to 1 over x to the P. Okay, and let's just restrict ourselves to like P greater than 0, because P less than 0 is going to be kind of silly. That's going to be a, you know, basically like x to a positive power, not in the denominator. But this thing is positive and decreasing, I'm telling you, and continuous on the interval from 1 to infinity. Okay, the larger the x value I plug in, the smaller this function is going to get. Does that make sense? It's like, what's the graph of this function going to look like? Well, like that picture I drew, it's going to go like this. Okay? Therefore, what's true about this series up here and the integral from 1 to infinity, 1 over x to the P? What does the integral test say is going to be true about the integral and the series? They behave the same. They behave exactly the same. So essentially, instead of looking at this series up here, we could look at the integral from 1 to infinity. We can go the integral from 1 to infinity, 1 over x to the P dx. Okay? And do you remember we already kind of did that like a couple of weeks ago when we were dealing with improper integrals? Do you remember what we found out about this? Where was kind of the cutoff point for this thing, to have this integral converge? Yeah, this thing converges for, converges for P greater than 1. And what happens if P is less than or equal to 1? Diverges or P less than or equal to 1. And that's even true if P happened to be less than 0. I mean, this thing is going to be stupid. Like, for instance, if I take P equal to -2, right? Think about it. If I took P equal to -2, 1 over x to the -2 is like x to the 2. Do you know what I mean? What's going to happen if you integrate x squared from 1 to infinity? Clearly, that's going to be an infinite amount of area. Yes? It's like integrating the parabola x squared from 1 to infinity. Clearly, that is going to have infinite area. So this integral converges for p greater than 1 and diverges for p less than or equal to 1. So can't we say then the exact same thing about this? The p series converges for p for what? For p greater than 1, and it diverges actually to infinity, right? For p less than or equal to 1. Okay? These two things behave exactly the same, and that's because of the integral test. The integral test for convergence. 1 over x to the b is clearly a positive decreasing continuous function, and we can apply the integral test to conclude things about the sum of the series 1 over n to the p for n equal 1 to infinity. Notice, do we know anything about what the series converge to if they happen to converge? Do we know what they add up to? No, no clue. We just know that they will converge if the power on n is bigger than 1. Okay, and by the way, so like what about this series right here? What about sum n going from 1 to infinity, 1 over n? What about that series based on this test? What happens? Does that converge or diverge? It diverges because what's p in this case? Yeah, p is equal to 1. So this thing diverges. Right? That's the harmonic series. That's the so-called harmonic series. Okay? And I promised that the harmonic series diverged. And what do you notice? The terms go where? The terms of this thing go to 0. And yet the series still diverges. What about this guy? What about the sum n going from 1 to infinity, 1 over n squared? What do you think about that? Does that series converge or diverge? It converges because p is equal to 2, which is greater than 1. This guy converges. We don't know what it converges to. It turns out it converges to something weird. It converges to pi squared over 6. If you like add up more and more and more terms to these things, turns out you're going to get really, really close to the number pi squared over 6. It's not clear at all why it adds up to pi squared over 6. That's a story for another day. What about this series? What about the series? What about series n going from 1 to infinity, 1 over the square root of n? What about that? What do you guys think about that? Diverge or converge? Diverges. Why? Yeah, this thing diverges because p is equal to 1/2, which is less than 1. Okay? It's a p series with power less than 1. Is this kind of making sense? We applied the integral test, and we get a whole host of information about these p series. 1 over n to the p series, right? Series 1 over n to the p. That thing diverges if p is bigger than 1, and it converges if p, or sorry, it converges if p is greater than 1, and it diverges if p is equal to or less than 1. Okay? And it diverges to infinity specifically. Okay? Any questions on that? The reason that rule works is because of the integral test, is the essence of what we're talking about here. Any questions on that? Okay, so again, here's kind of the statement of the convergence of a p-series. This is theorem 911 in the book. Okay, sum in going from 1 to infinity, 1 over into the p, converges for p bigger than 1 and diverges for p less than or equal to 1. By the way, do I really care that much? Like, do I have to put the restriction on here that p be positive? Is that really necessary? No, even if p is negative, this thing stupidly will still diverge, yes? Because it will be things like the sum of n squared, for instance, which clearly the terms are like going to infinity. The terms are going to infinity. They are not going to 0, and therefore the series would still diverge. Oops, I didn't mean to erase the entire thing here. Okay, what did I mean to do? I meant to erase that thing right there, yes? I don't necessarily need p greater than 0. P just has to be equal to or less than 1 for the p series to diverge, okay? What about this? I mean, I just want to make sure we're on the same page here. What about this? And think about this with your friends around you. Sum in going from 1 to infinity, 1 over n times the square root of n. What do you think about that? Okay, so think about that with someone right next to you for a minute. Okay, n times the square root of n. Right, so okay, so in this case, the claim is that this thing actually will converge because what's the power on n really once we kind of do a little bit of algebraic manipulation here? Yeah, because it's into the 1 times into the 1/2, which is into the 3/2. Right, so this is a p series, right? So our p here is 3/2, which is greater than 1. So this thing converges. And we don't know what it converges to necessarily. By the way, doing the integral from 1 to infinity of 1 over x to the 3/2, that doesn't tell you what the thing converges to, right? We already said that the integral value and the series value are not necessarily the same. Does that make sense? But you would get a finite value if you went ahead and did that integral, but that value you got wouldn't be equal to the sum of the series necessarily, okay? So all we can say is that this thing converges because it's a p series with p equal to 3/2. All right?